So I'd like to kind of wrap up with some recent advancements and a little bit about where we're going from here. So photon sources are critical in any quantum communication system. Right now we have demonstrated entangled photon pair sources deployed on satellites back in 2016 with the Messier satellite, for example. So where do we go from there? So in the near term, medium term, entangled photon sources should be developed to leverage multiplexing. So for DWDM technology, for broadband sources, let's leverage the frequency band. And then as we move further and further, let's move from just entangled photon pairs to hyper-entangled states, multi-dimensional entanglement. And then from there, we can develop protocols with fewer and fewer trust assumptions on nodes. And something that's really important is we need to do co-development between photon sources and quantum memories. So that interface is extremely important to make a scalable quantum internet. We need to have our sources, efficiently interfacing with our quantum memory systems. Photon detectors are also extremely important. We need to detect these quantum photons, right? So if we're mounting detectors on satellites, as I mentioned before, radiation is something we have to think about, and radiation does have an effect and it does degrade the quality of our photon detectors. As I mentioned earlier, we need these systems to be reliable and to be self-calibrating and self-healing. So here's I wanted to highlight a project from a couple years ago out of IQC and with many other collaborators, where they studied silicon avalanche diodes, photodiodes, for photon detection. And they actually used an in-orbit laser annealing approach to self-heal from radiation damage. So this is, technologies like this are really important for kind of pushing the boundary to the next generation of photon detectors for satellite deployment. Quantum memories are extremely important as well in scaling quantum systems and quantum networks. I'd like to highlight a few different promising platforms for quantum memory. So there's warm vapor, there are laser-cooled atomic systems, cold atoms, rare earth ion-doped crystals. These are all different ensembles for being able to capture that photon and store it and retrieve it on demand from the quantum memory. And quantum memory really enables a whole suite of protocols that you can't do without this storage capability. And I'd also like to mention photonic integrated circuits. And photonic integrated circuits are a very promising technology because of their footprint, and especially when we're talking about quantum satellites and deploying this technology in space. Photonic integrated circuits are great because they're on a chip and they're light, they don't consume a lot of power, and they have all the optics functionality built in. So this is a relatively new technology that we have seen some recent advancements and a lot of investment in startups in this space to really increase the footprint of functionality that these chips have for quantum networking. And that being said, a lot of that work is being done in quantum computing land. So photonic quantum computers, they need this functionality as well. So if they're able to push that frontier forward on the computing side, then they may very well serve as great candidates for a quantum satellite.